Welcome back. Today we cover more identities, including sum and difference formulas. Quiz 7 was today. Just want to point out project number 7 is collected next class, and project 8 will be assigned next class. Number 1, we start this section by solving equations that require the use of identities. It's easiest to solve trig equations if we can write everything in terms of one angle or of one trig function. Let's solve the equations below on the interval 0 to 2 pi. Okay, 3 sine of 2x minus 2 sine of x equals 0. All right, so the difficulty here is that we have two different angles, 2x and x, and that doesn't work out so well. So we need to get it so that they're both functions of just exactly the same angle. So we're going to make use of an identity. I'm going to copy the 3, I'll copy the minus 2 sine of x, and I'll copy the equals 0. But we have an identity that tells us what sine of 2x is. It's really, it's really 2 sine x cosine x. So that's one of our double angle identities. And even though this equation looks a little bit messier than it did before, the nice thing is that all of the angles are exactly the same, x, x, and x. Okay, let's clean this up just a little bit. This is really 6 sine x cosine x minus 2 sine x equals 0. One thing you might do is add the 2 sine x to both sides. I'm not a big fan of doing that. I'm a much bigger fan of leaving 0 on one side of the equation and then factoring the other side. If the left-hand side is factored, then we can set each of the factors equal to 0, and that's what we'll do here. So what can we factor out of both terms in this left-hand side? Well, we can take out a 2, and we can take out a sine x. And then we need to fill in the parentheses. So the first term is left with 3 cosine x, minus the second term. Pretty much everything is factored out, so that's just a minus 1. And now because we have this equation in factored form, we can set each of the factors equal to 0. So either 2 sine of x is 0, or 3 cosine of x minus 1 is 0. And then we have to separately solve these two equations. Okay, so divide both sides by 2 here, and we get sine x equals 0. And I guess you could think about taking inverse sine, but I'm hoping that we know the places where sine of x is equal to 0. We're trying to solve this equation between 0 and 2 pi. There are 3 different answers here between 0 and 2 pi. We have x equals 0, x equals pi, and x equals 2 pi. And then the other equation, add 1, and then divide by 3. And I'm hoping you don't know what angles make that true. So here we do need to use the inverse cosine. So let's use our calculator to get an estimate for this angle. Again, check your mode. This problem is in radians, 0 to 2 pi, so we're fine. So we'll get one fundamental angle right there. 1.231, we'll say, radians. And then to find the other one, we need to draw our familiar unit circle. 1.21 or 1.2 radians is in the first quadrant. So 1.2. This is a cosine problem, and we know that x is the important thing when you're solving a cosine problem. So that x is the same as that x. So then the real angle that we want is going to be this one going around here. You could go the backwards way, but that would give you a negative answer. So you could just say negative 1.23, but that's not between 0 and 2 pi. So we don't want to go the backwards way. So this angle that we want here is equal to 2 pi minus the 1.231. So about 5.052. Okay, so then I'll highlight all the different answers. We had these two answers from the second equation, and then these 3 answers from the first equation. So 5 answers altogether. Certainly you can use the graphing capability of your calculator to check and see that you get those 5 answers. Part B, cosine of t equals sine squared of t. So the problem here isn't that the angle is different, because the angle in both trig functions is just t. They match each other, which is great for us. But the difficulty is that you got two different trig functions here, cosine and sine. But if we take a look at this little hint up here, it says in bold, one angle, one trig function. So having both of those sine and cosine there is problematic. So there is an identity that relates the sine squared to cosine squared. So we know that Pythagorean identity says sine squared t plus cosine squared t is always 1. So solve that for sine squared, and we get 1 minus cosine squared. So then we can just take our original equation and replace the sine squared with 1 minus cosine squared. So this becomes cosine of t equals, instead of sine squared, 1 minus cosine squared. So this is better because now this trig function, this trig equation has only cosines in it, not sines in it, not sine and cosine. Okay, I really want one side of this equation to be 0, so let's bring everybody to the left. Add cosine squared to both sides. I'll copy the cosine t, subtract 1 from both sides, and that's how we get our 0. And that right there is a quadratic equation, or it's an equation that's in quadratic form, maybe is the way to say it. So this equation reminds me of y squared plus y minus 1 equals 0. So if we're lucky, we can factor. I don't think this one does factor, but you can spend a minute trying to factor. So if it doesn't factor, then quadratic formula is our recourse. Okay, so normally the quadratic formula says x equals, but now it's y equals negative b plus or minus. You know the rest. So let's plug in all the different pieces. So we go negative 1 plus or minus square root of b squared. That's 1 squared minus 4 times 1 times negative 1. 1 minus negative 4. Divided by 2 times 1 is just 2. So it's negative 1 plus or minus root 5 over 2. Okay, so I introduced y in this problem just to make it look like a more standard looking quadratic equation. But really what this means is that not y, but cosine of t is equal to negative 1 plus or minus root 5 over 2. Because that's what I replaced y by. I guess I replaced that with y. Okay, so let's take a look at what these numbers are on the calculator here. So we go negative 1, I'll do the minus first, minus root 5, and then divide that answer by 2, and we get that. And then I'll do the same thing, but with a plus, and then divide by 2. Okay, so we have cosine equal to these two different numbers. Cosine t equals, on the one hand, negative 1.618. On the other hand, 0.618. And it feels like we're doing inverse cosine to both of these equations, but one of these equations is kind of silly and has no solutions, so I'm hoping that we start to recognize that cosine equals negative 1.6, has no solutions at all. Cosine doesn't get any smaller than negative 1, so I can just put down here, no solutions next to this one. But the other one does have solutions, so let's go ahead and find the two solutions. So inverse cosine of this 0.618 answer that we have on the calculator. We're still in radian mode, so that's good. So one answer is 0.904. We've got to find the other fundamental answer. It's the same unit circle picture, but instead of the 1.2 that we have here, this now becomes the 0.94 that we just saw. So then the other answer is 2 pi minus 0.94. So without drawing a unit circle, because it's so similar to the problem we just did, we'll just do 2 pi minus the answer. Whoopsies. 2 pi minus the answer. Okay, so now I've already forgotten what the other answer was, so let's get that back. Okay, so 0.5378 and 0.905. So we'll highlight. Those are our two answers to the original trig equation. Again, you could go back to this original trig equation here and graph both sides on your calculator and intersect, and hopefully we should get those same decimals. Number 2, here are some more identities for your enjoyment. These are called the angle sum and difference identities. For example, cosine of one angle minus another angle is equal to cosine of the first angle times cosine of the second angle plus sine of the first angle times sine of the second angle. All right, so there are 4 identities here. Certainly when you're taking the quizzes or tests, you can write these things on your reference sheet and that's fine. But if you gain some familiarity with them, that's a good thing. So just pointing out some patterns here. For cosine, a minus between the angles turns into a plus over here, and a plus between the angles turns into a minus. But for sine, the sign actually just gets copied down. A minus between the angles gets copied here, plus between the angles gets copied here. For cosine, it starts off cosine, cosine, and then sine, sine. Cosine starts off cosine, cosine, sine, sine, but sine is a little bit more equal opportunity, and it gives you a sine and a cosine in each term. Sine and cosine, sine and cosine. So it is possible to memorize these 4 equations without too much work because there are some easy patterns in there. 3, we're going to prove the formula for cosine of a minus b by following these steps right here. So take a look at the diagram on the left-hand side. So the first thing is that we've got this angle right here is marked as b. This angle right here is marked as b, which means that this point right here is cosine b sine b. That one tells me that I'm on the unit circle there. And then the bigger angle is a, so we know that this point right here is cosine a comma sine a. So far, so good. So let's just focus on that diagram right there. And what we're going to do is find the distance, this is part A, the distance between the 2 points on the circle above left. So the 2 points that are up there in red, and we know our distance formula is you're supposed to subtract the x coordinates and then square, and then you're supposed to subtract the y coordinates and square, add them up, and then take the square root of the answer. So let's give that a shot here. So the x coordinates, cosine of A minus cosine of B, and then square. So that's the difference of the x's plus the difference of the y's. Sine of A minus sine of B squared. Okay, so let's go a little bit further with this thing. So big old square root here. And we're going to FOIL out both of these things that are being squared. So cosine A minus cosine B squared is cosine squared of A minus 2 cosine A cosine B plus cosine squared of B. So if you don't see that, then pause the video and write cosine A minus cosine B times cosine A minus cosine B. FOIL it out and you should get what I've written. Now we'll do the second one. Plus sine squared A minus 2 sine A sine B plus sine squared B. Okay, so it's a whole lot worse now that we FOILed it out, but good things happen because, for example, here's a cosine squared A plus sine squared A. And how much is cosine squared A plus sine squared A? No matter what A is, it's always 1. Likewise, cosine squared of B, this other angle, plus sine squared of B is also 1. So what we have left then is, let's see, square root of, so the one yellow plus the one blue is 2, minus, and then I'll copy the other terms, 2 cosine A cosine B minus 2 sine A sine B. Okay, so there isn't really much further we can go with that. You could factor out the 2 if you wanted to. I think we'll do that at the end. But anyway, that's the distance between the 2 points in the picture at the top left. Part B says, now rotate the 2 points on the circle by b degrees clockwise to get the picture above right. So we're going to take this entire diagram right here, we're going to rotate it b degrees clockwise. So this line will land perfectly on the x-axis, which is why we don't see it here anymore. This line is just going to rotate by b degrees. I don't know where, I mean, it's not going to land here, but it'll land someplace, maybe here. And so that's this line right here. And then how much is the angle then between this line and this line? Well, it's the same as the angle between these two things here. And the angle between those things is just a minus b, right? So this angle in here is just a minus b. And we know that because we're on the unit circle, we can just say, well, hey, wait a minute, if you give me an angle, then the point is going to have coordinates cosine of the angle, comma, sine of the angle. So there they are, cosine of a minus b, sine of a minus b. So the next thing to do is to find the distance between these two red points right here. We're just going to find the distance between those points. So again, we're going to do the distance formula, but now one point is this one, and the other point is 1, comma 0. So let's give this a shot. Okay, so this distance is now, highlight part B is starting here. Okay, so this distance is square root of, okay, so we're subtracting the x coordinates. One x coordinate is cosine a minus b, minus the other x coordinate is just the number 1, that gets squared, plus, now we subtract the y coordinates. The one y is sine a minus b, minus the other y is 0. We were at the point 1, comma 0, and that gets squared. Okay, let's expand this out. So we go cosine squared of a minus b minus 2 cosine of a minus b plus 1 plus, and then the second term is just sine squared of a minus b. And that's all under the square root, and then a good thing happens here because this cosine squared of an angle plus sine squared of exactly the same angle is always 1. So that means that this whole thing is square root of 2 minus 2 cosine of a minus b. Okay, so we'll stop there. Again, you could factor the 2 if you wanted to. So what do we have here? Well, we have two different distances that we've just calculated. We found the distance between the red dots right here. That's what we did first. And then we found the distance between these red dots here. But what must be true about the lengths of those two red line segments? Well, they're equal, right? All we did was rotate a picture. And when you rotate, lengths don't change. They're preserved. So that means that the two distances that we calculated must equal each other. So this thing right here, that final purple, must equal this final black. And so let's see if we can write that down and maybe not write too much else. So they are equal. That must be true about our two distances. So then we write the big purple and it must equal this black expression here. Okay, let's see if we can do some nice algebra in our heads. So we're going to square both sides of this equation, which means that the square roots cancel. And then we're going to subtract 2 from both sides of the equation, which means that these 2's cancel. And then we're going to divide everything by negative 2. So that negative 2 becomes a positive 1. That becomes a positive 1. That becomes a positive 1. And then we're going to write down the final thing that's left. So this becomes cosine of A, cosine B. That minus 2 also became a plus 1. Sine A, sine B equals, that minus 2 became a 1. And there you have it. That's the very first identity in our list from the previous page. Okay, so you don't need to recreate this, but I just wanted to show you that that first identity is true for valid reasons other than my math teacher says so. Number 4, the good news is that the other 3 sum and difference identities follow very quickly from the identity we just proved. Think about this later, and then there's a hint that you're going to try to employ. But we just did one of them. The first one is the hard one, but the other 3 identities on the previous page all follow pretty quickly from this one that we now believe to be true. 5, how can we use these sum and difference identities? First, we can easily prove our double angle identities. Sine of 2 theta is 2 sine theta cosine theta, and then this other one with cosine of 2 theta. So last class, I promised you that we would prove these identities, but I asked you to just hold off suspend judgment on them until today. So now we're ready to prove them. So sine of 2 theta, we're going to pretend we don't know that it's 2 sine theta cosine theta. There's no reason for us to believe that from last class, but we'll prove it now. So one thing we definitely believe is that 2 theta is the same as theta plus theta. And then we can use our sine of a plus b formula. I'll put it here. And all we'll do is we're going to replace this a with theta, and we're going to replace this b also with theta. So every a and b becomes theta. So this is equal to sine theta cosine theta plus sine of theta cosine theta, which is really just 2 sine theta cosine theta. And that's it. That's one of our double angle identities from last class, now proven. Same thing for cosine of 2 theta. Maybe I'll just leave that as an exercise. Cosine of 2 theta equals, it's going to start the same way. Rewrite 2 theta as theta plus theta equals some miracle, and then hopefully at the end we get the identity that we looked at last class. So maybe pause the video now and give that a shot, and then come back when you're done. Moving on to part B, we can now find exact angles, exact values of many new angles. What's the exact value of sine 75 degrees? Okay, so first of all, I want to just point out that 75 degrees is not one of the special angles that we know about, right? We know 30, 60, 45, and then lots of multiples of those things. We definitely don't know anything about 75. Let's see what the calculator has to say about 75. Again, you hit one of those buttons, you think about the mode. Okay, so it's not anything that looks nice to me, but let's see if we can't use one of our new formulas to figure out what that decimal really is. Okay, 75 degrees, I don't know what's going on there, but I do know that I can write 75 degrees as a sum or difference of two angles that are important on our unit circle. So there are multiple ways to do this, but for example, if you take 30 and add 45, you get 75. And the good thing is that we know an awful lot about 30 and 45. So using our formula that's still up here at the top of this page, we just change the A's to 30s and the B's to 45s. And we get that. But all four of these are known. They're all on the unit circle, right? So sine 30, that's half. Cosine of 45, root 2 over 2. Sine of 45, also root 2 over 2. Cosine of 30, root 3 over 2. Mushing the multiplication together, we get root 2 over 4 plus root 6 over 4, right? We can multiply those two radicals together inside. And then we'll just combine fractions. And there we have it. Sine of 75 degrees is exactly root 2 plus root 6 over 4. Do you believe it? I don't know if I believe it, but I can type that in over here and see if we get something that looks good. Root 2 plus root 6 divided by 4. What are we hoping to get here? Well, if we did it right, we better get that decimal that's sitting right up above. And we do. So this, the sum and difference formulas that we just got kind of open up a whole new world of nice angles that are on the unit circle. You can take any angle that you already know about, add or subtract any other angle that you already know about, and you can get more angles that you know about. And 75 is now in our list of angles that we know about. I'm not saying 75 is as important as 30 or 45 or 60, but I'm just saying that these new identities allow us to do more, to figure out more exact values of trig functions of angles. See, we can create new identities. Let's find the formula for cosine of theta plus pi over 6. Okay, so using our cosine formula, there's a plus sign in between there. So see if you can pause the video here and fill in using the cosine sum formula and then come back. Okay, so this is a cosine. So cosine starts with cosine, cosine. And with cosine, it's the opposite of the symbol in the middle. The angles here were added, so the formula has a subtraction, and then it's a sine sign. Okay, this equals cosine theta. Okay, cosine of pi over 6 is, what is cosine of pi over 6? Is that root 3 over 2? And then minus sine theta stays, and then sine of pi over 6 is half. And right there we have a new formula. Cosine of pi plus theta over 6, sorry, theta plus pi over 6 is cosine of theta times root 3 over 2 minus sine theta times half. And that's it. B, or sorry, 6. Can we go backwards from the above calculation? Said another way, if I give you root 3 over 2 cosine minus 1/2 sine theta, which is exactly this, right? Just terms shuffled around a little bit. Can you rewrite the whole expression as a single sine or cosine function? So if I gave you this complicated thing, could you work backwards and say, oh, Ian's just playing games. That's really just cosine of theta plus pi over 6. What if the coefficients aren't equal to cosine of some angle and sine of the same angle? So this one worked out. Maybe we just get lucky and we recognize, oh, that's cosine of pi over 6. And this one right here, oh, that's sine of pi over 6. So then we have these two things, and then we can put them back together using the cosine sum formula. But what if these numbers aren't cosine and sine of some angle, respectively? So for example, down here, can you rewrite this thing as a single sinusoidal function? I mean, let's see. So going back up, so I see a -2 touching the sine function. So that's kind of like this -1/2. But -2 is definitely not the sine of some angle, right? There's no way that this could be a -2 if it came from sine, because sine never gets less than -1. So, okay, that seems tricky. Is it even reasonable to expect that it's possible? Let's go ahead and graph this thing on the calculator and see what it looks like. So we'll change the t's to x's here. Okay, degrees of radians doesn't much matter here, but I'll put it back into radians, and then we'll look at our window. Let's go from, say, -2 pi up to 2 pi. You know what? Let's not do that. I did that because I know what's going to happen. So let's just go back to -10 to 10. Okay, so we'll graph here. So we're looking at -2 sine t minus cosine t. Well, gosh, that doesn't look nearly as complicated as I was expecting. We had some sine function coupled with some cosine function. They both had coefficients. We added them together or subtracted. And it just looks like a sine or a cosine, like an ordinary sine or cosine function. So maybe it is possible. Maybe it is possible to rewrite this function right here just as a sinusoidal function. Sine, maybe the period is messed up, maybe there's a horizontal shift, maybe there's an amplitude change, but it just looked like a generic old sine or cosine function shifted around a little bit. Okay, so we're going to make this very general. Instead of trying to write this specific thing as a single sine function where we find a and b and theta, we're going to say, okay, what if you just had a1 sine of bt? So a1 is this -2 here, and a2 cosine of bt, and a2 is that -1 there. So I think I just answered this question here. So a1 is the thing touching the sine, which is -2. a2 is touching the cosine, that's -1. So our job is to try to rewrite this complicated looking thing where the a1, well, this whole thing will be given to us, and we want to try to rewrite it like this. Finding a, finding theta. I guess that b is probably given as well. It's whatever number is in there. Number 8, the derivation below is going to stretch your math muscles. Embrace the struggle. Okay, so taking a look again at the goal, we're given this thing, and we want to rewrite it as this thing, which means try to figure out A and try to figure out theta. Okay, let's give it a shot. I'm going to start with the right-hand side. A sine of bt plus theta equals. I'm going to copy the A, I'm going to put big brackets, and I'm going to say now, today we have talked about a formula for the sine of something plus something. So let's go ahead and use our sine sum formula and fill in the blanks. Pause the video here and come back when you're done. Okay, so this is a sine, so it starts sine cosine. So sine bt cosine of theta. Sine copies the sign, so a plus between the angles means there's a plus in the formula. And then it goes sine of the other thing, sine theta cosine of bt. Okay, and let's go ahead and distribute that A through. Okay, so we've done that, and now let's go back again and look at the goal. We were trying to make this crazy thing equal to what was given to us, but this crazy thing turns out can be expanded to that crazy thing. So ultimately we want this to equal this. And then let's see, there's actually some stuff that's kind of the same. So I see a sine of bt here and a sine of bt here. And I've got a cosine of bt and a cosine of bt. So it seems like if we're going to make these things equal, then probably we want this thing to match up with this thing, because they both have a sine of bt in them. And then the whole other thing to match up with the rest of this. And so if that's going to be the case, kind of in our heads, we're going to equate the two purple things and then separately equate the two red things. And if I equate the two purple things, then the sine of bt is the same in both, right? I can kind of ignore this part and just say, oh, the a1 had better equal a cosine of theta. So let's write that. a1 is going to equal the a cosine of theta. And then a completely separate equation from the red things equaling each other. In that case, what's the same in both? It's cosine of bt. So we'll ignore those and make the other stuff equal. So the other stuff is a2 equals a sine theta. Okay. There are four variable looking things in here, a1, a2, capital A, and theta. We've got to be clear what's given. What's given is the left-hand side. So the a1 and a2 are known. We're trying to find a and theta. So ultimately, we need to solve these equations for a and theta. Let's solve for capital A first. I'm going to do something kind of strange. I'm going to square both sides of this equation. And when we square the right-hand side, don't forget that each of the factors gets squared. And I'll do the same thing for the second equation. And then I'm going to add them together. So squaring was strange. Adding continues the strangeness. But bear with me. And then on the right-hand side, I'm going to factor out that a squared. Copy the left-hand side. And then, oh my goodness, finally something useful, something that we can grab onto. Cosine squared plus sine squared. I've seen it a million times. It's just 1. So the whole right-hand side just becomes capital A squared. And again, we were trying to solve for A, so I think we're right there. Just take a square root of both sides. Okay, technically it should be a plus or minus in between, so I'm going to kind of put this equation here in parentheses. I actually would stop here at this equation and just say, all right, find the value of A looking at that equation. I typically would pick a positive A every time, and we'll see this formula in another context soon enough. So it's a little detailed. Don't worry about the plus or minus for this one. But anyway, there's a capital A. And then to find theta, it's actually easier. So let's go back up to my two green equations here. I'm going to divide the second equation by the first equation. So the bottom equation divided by the top equation equals bottom equation divided by the top equation. And what nice thing happens here? Well, the capital A's cancel. So we just get A2 over A1 is sine theta over cosine theta. Trying to find theta. So look, sine over cosine, we've seen that before. Sine over cosine is really tangent. And we're trying to find theta, so I guess take the inverse tangent of both sides. Not going to write that. I'll just say stop there and then solve that, but it just involves taking inverse tangent. Sometimes you have to be a little bit careful when you take inverse tangent, but we've got our two equations. And in fact, they're just written down here in number 9. It says if you start off with the givens that we did, then capital A squared is A1 squared plus A2 squared. That's here. And tangent of, no, I don't know why it changed to a phi. Let's just call it math magic. But tangent of theta is A2 divided by A1. A2 divided by A1. Okay, like I said, we'll see these formulas in a different context soon, but it's not too early to start being exposed to them. 10, let's use our new formula to rewrite -2 sine t minus cosine t as a single sinusoidal function. We'll have to think about what quadrant, again, it's phi, it should be theta, should be in. Okay, let's give it a shot. So what do we know? We know that the A1 is the number touching the sine, so that's -2. And A2 is the number touching cosine, which is -1. So if I wanted to find capital A, I'm going to use the formula A squared is equal to A1 squared plus A2 squared. So that's 4 and 1 are 5. So that means that capital A is the square root of 5, technically plus or minus, but I always pick A to be plus, positive. Okay, and then to find theta, or phi, what I called it here, I just use the second equation, it's right here still. Tangent of theta is A2 over A1. So let's write that. Tangent theta is A2, that's -1 divided by A1, -2. Okay, so let's type into the calculator here. We're going to find the inverse tangent of a half. Those negatives cancel. Okay, so we're doing inverse tangent of a half. And let's go ahead and be in radian mode for this problem. And we get 0.4636, so that's theta. And I'm just going to go ahead and write that angle down and put it in a unit circle. So this one tells me that theta is 0.4636. So we'll draw our old friend the unit circle. 0.4636 is in the first quadrant. That's that angle in there. But there's a little bit of an issue here because we said there's always these two fundamental angles, and so that's one of them, and the other one is in one of the other quadrants. But let's come back up here. Where did we have it? So these green equations. That's what I want to look at. So I'm going to write this and then I'll erase it. But what we just figured was that in this problem, A1, which was A1, was -2. So this equation right here becomes -2 is equal to, and then the A we found was root 5, and then times cosine of theta. So that means that cosine of theta is -2 over root 5, right? Okay, wait a minute. But if cosine is negative, then does this angle we drew in the unit circle make sense? If you're right here, is the cosine positive or negative? Well, cosine is the x, and it's a positive number, so this ain't it. That's not the angle that works. It just doesn't make sense from, it makes sense for the tangent equation, but it doesn't make sense for the equations that we started with. Okay, so this is some x and y, and we know that tangent is y over x. So what we're looking for are places where the y over x are the same numbers, but we got to make sure when we divide them, we still get the same sign. So at this point right here, x and y are both positive, and when I divide them, I get a positive number. At this point, though, the x turns out to be a negative number, and the y is positive, and when I divide, I get something negative. Over here, if you go straight down, The x stays positive, but the y changes. When you divide, that's still a negative number. But then when you go to the diametrically opposite point, the x and y are both negative, and when you divide them, you get something positive. So that's our winner down there. So we're going to extend this line and then say the actual angle that we want is really this one. And we know the 0.46 gets copied in here by symmetry. And so, so pi plus 0.46 is the actual angle that we want. So about 3.6. Okay, so that's it. That's our winner. So what does that mean? That means that this theta is 0.46 was not right. It's really 3.605. In fact, we probably could have known that we were looking for something in the third quadrant because there was a -1 and a -2, and somehow that actually corresponds to this point down here. Okay, so what does that mean? It means that we can take this guy right here, -2 sine t minus cosine t, and rewrite it as a single sine function. So let's get the pieces in the right spot. So I'm looking at this thing right here. This is what we calculated. So the a that we found goes first. Capital A was √5. A single sine function times bt. Okay, so b is just whatever it was 1 in this problem. B is the number that's in front of the t's. You can see it right here. B is there. So it's just 1. So sine of 1t plus, and then the theta or phi that we just found is this 3.6 business. Plus 3.605. Okay, so what we have here typed in is the original, -2 sine t minus cosine t. I'm going to come down here and I'm going to type in the new function that we just found, second square root of 5 times sine of x plus 3.605. I'm going to go back up and I'm going to change this thing to make it thicker, because if we did it right, then this thing should just trace out that, that function that we drew before. Fingers crossed. Oh, good. Okay, so this is a little bit of a process. Like I said, it's going to stretch your math muscles, but I kind of like it in that we took something that was quite complicated, -2 sine t minus cosine t. We looked at the graph. Surprisingly, it looked like it was just some ordinary old periodic sine or cosine function, and then we found it. Turns out that this thing is exactly √5 sine of t plus 3.605. And that's really nice because if, for example, I wanted to set this equal to, I don't know, like 7, well, that's really hard to solve that equation. In fact, I have no idea how to solve that equation other than to do everything that we just did and then solve this simpler expression equal to 7. And solving that expression equal to 7 is something that we have experience with. We can do that. So I kind of like it, taking these two trig functions that are kind of complicated with a subtraction symbol between them, rewrite it as a single trig function, and then you could work with it in its simpler form. Okay, last problem here is 11. Create identities for the following expressions. Int first use an identity. Okay, there are 4 of them here. This isn't indicated as being a separate activity, so I'll just include it here in this video. But I would say maybe pause the video here and really work through these to the best of your ability before you come back and check out the rest of this video. Okay, let's take a look at part A. This is a sum sine formula. I go sine of the first thing, cosine of the second thing, plus, copy the symbol, sine of the second thing, cosine of the first thing. And then just replace the things with pi in it. Sine of pi is 0, plus cosine of pi is -1. So this is really just negative sine of theta. And we won't do it here, but you might ask yourself if the graph, if this fact is reasonable. If you think about what the graph of sine of pi plus theta looks like, should be able to figure that out without the graphing calculator, and see if it agrees with what the graph of pi equals negative sine theta looks like. Okay, next one, same idea. Sine of the first, cosine of the second, but now we copy the subtraction symbol. Sine of the second, cosine of the first. Notice that the second doesn't have a negative theta in it, right? It's just theta. The subtraction symbol is taken care of by the nature of the formula. Okay, sine of pi is still 0. Minus sine of theta, cosine of pi is still -1. So this is really just positive sine of theta. Okay, sine of the first, cosine of the second, plus, copy the sign, and the sine of the second, cosine of the first. Sine of pi over 2 is 1. So this one just becomes a 1 cosine theta, plus cosine of pi over 2 is 0. So this is really just cosine of theta. And you might ask yourself if that's reasonable. If you think about what the graph of sine of pi over 2 plus theta looks like, it should be an easy transformation from just the graph of sine theta. Does it land exactly on just the graph of cosine theta? Hopefully it does. Sine of the first, cosine of the second, minus cosine of the first, sine of the second. Okay, sine of pi over 2 is still 1. This is a minus. Cosine of pi over 2 is still 0. So maybe surprisingly, maybe not, this is also cosine of theta, and you might ask what's going on there. Thinking about the graph of this is quite a bit more complicated. It's not just a simple one transformation from the original. So that's tougher. But somehow, some way, it's going to land right on cosine of theta.